Welcome back to today's video. In today's video, we're going to discuss feature scaling as well as transformation pipelines in scikit-learn. Before ending today's video, make sure you hit the subscribe button down below and like the video for more content just like this. Let's get right into it. And so let's discuss feature scaling in scikit-learn, or in general, rather. Feature scaling basically is taking a look at data values that may not be consistent within a constant range and trying to take that data that is not within a very constant range in different data fields and push that data into a constant field. Let's take a look at our housing CSV file. If you take a look at, for example, the total rooms and compare that to the latitude, what you'll notice is that what's the range of the latitude and what is the range of total rooms? Well, just skimming through this data, what you can notice about the latitude is that the latitude, typically speaking, ranges anywhere from 30 all the way anywhere up to 40, right? If you take a look at the latitude. Then you take a look at the total bedrooms data field. And this data field typically looks like it ranges from anywhere from 100 all the way up to around 1,200 or so. Now, when our machine learning model takes a look at this data, it is not able to really determine what is the correlation really between latitude and total bedrooms because this data is not within the similar range. And so what feature scaling basically does is it pushes the data in all the different data fields into a consistent range between an X number to a Y number, rather than having each individual data field have its own range. In this case, total bedrooms has a specified range. And remember, the range is just the min and the max value. And we would obviously subtract the min from the max. But in terms of if I were to ask you for a closed interval of the range, you would say it's the min value and then the max value for each individual data field. Okay, so in this case, you have 13 data fields or so. And so you're going to have 13 ranges, right? But what we want is we want a machine learning model to be able to observe patterns within this data. And so because of that, we wanted to have a consistent scale. Typically speaking, of 0 to 1, or we might standardize the data in some way whatsoever. There are two methods that we're going to be looking at in order to create a constant scale for our individual data fields. The first one is min-max scaling. Now, min-max scaling is a way to standardize, or to normalize rather, our data, but it does have a few problems that we're going to look at. What min-max scaling basically does is it takes a given data instance and it subtracts it from the min data instance in that particular data field. Now, when I say data field, I'm referring to an entire column of data. And when I refer to a data instance or a data value, I am referring to an individual value within a data field within our CSV file. And so what it does is it takes a given data instance within some data field and it subtracts the min value for the minimum data instance that is observed within that entire data field and puts that over the maximum data instance observed within that given data field and subtracts it from the minimum data instance from that data field. And so in this case, taking a look here at, for example, a more relevant data field, which would be like, say, for example, median house value, we would take a given house value. In this case, let's take the first house value, and we would subtract this, subtract the minimum house value, right, from this data instance and put it over the maximum house value minus the minimum house value. When we do that, we're going to be able to get an x value, an x scaled value, x subscaled value that is between 0 and 1. Now, one of the problems with using this approach of min-max scaling is that the data might be heavily influenced by outliers. Now, we know what outliers are. Outliers are simply data values that are outside the general trend of our data. Now, if you want to use, for example, a box plot, you can observe the inner quartile range and be able to observe values that are outside of that inner quartile range when we take a look at some data instances. But forgetting that for a second, generally speaking, if you see some data that is following a particular trend, and you see that there's a data value that is extremely outside of that general data trend, you can easily deduce from that observation that that data instance is an outlier. Well, the same thing applies to min and max values. The min value and the max value are the most likely data instances that are going to be outliers, typically speaking, right? In terms of that particular column. In terms of each particular column, the min and the max value are going to be most likely to be the outliers. Now, they might not be outliers when you compare it to the general trend of the data, but for each particular column, it will be an outlier. And so it may be an outlier. It might not always be an outlier, but it may be an outlier. And so it could be heavily influenced by an extremely low or an extremely high house value, or an extremely low or extremely high latitude or longitude. And so that's one of the problems that we have with min-max scaling. Now, it does put the data between 0 and 1, and that does allow the machine learning model to observe correlations between our data without, just creating some random answers. And so this class scikit-learn actually provides a min-max scalar transformer, and the feature underscore range allows you to change the range, meaning that this particular property within the class allows you to change the range from 0 to 1 to maybe, let's say you want -1 to 1. We know that the Pearson R correlation coefficient had a range from -1 to 1. But the min-max scalar transformer allows you to do that in this scikit-learn library. And so that's what min-max scaling is. The scaling that we're going to use is called standardization. Standardization is basically taking a given data instance and subtracting the mean in that data instance, and then putting that over the standard deviation. Now, let's take a look at each of these values. So we have here that z is equal to x minus mu over sigma. What is x? Well, x refers to a given data instance, mu refers to the mean, and sigma, which is in this case the symbol that you have right over here, refers to the standard deviation. Now, what is standard deviation? Standard deviation is, typically speaking, the spread of the data. Now, there is an equation for standard deviation that you don't necessarily need to know, but it basically measures what's the spread of the data. Mu refers to the mean. Why is calculating for the mean better than just taking the min and the max value? Well, calculating for the mean, remember, is not very affected by outliers. It is a robust statistic. It is a robust statistic in that it is not very much affected by outliers because it takes a look at all the data instances and is less affected by outliers. Now, it is still potentially affected by outliers, obviously, but it is less likely to be affected by outliers than using the min-max scaling. And then x refers to that given value, obviously. So this is obviously less influenced by outliers compared to min-max scaling. It also rescales the data so that the data has a mean of 0 and a standard deviation of 1. Okay, now you might be thinking about z-score, and if you remember, z-score is used to represent the percentile in a bell curve. So typically speaking, if you have a bell curve, if you've ever seen a bell curve, typically speaking, is data that is symmetric on both sides of the data. And that type of data is referred to as normalized data. And the z-score is used to represent the percentile such that beneath that percentile, we have a certain area of data, okay? But in our case, we're not actually going to be converting this data into a bell curve distribution because our data simply is not a bell curve distribution all the time. Now, it may be a bell curve distribution, but it is not always a bell curve distribution. And so because of that, what we're going to be focusing on is getting a mean of 0 and a standard deviation of 1. That is our goal, a mean of 0 and a standard deviation of 1. Okay, but we're not going to be converting it into a bell curve distribution because our data simply may not be bell curve. Now, it may be bell curve, but we are not necessarily given any certainty surrounding that. Now, scikit-learn does provide a transformer. And again, all this math that we're discussing, you don't necessarily need to know it. It's just more high-level ideas that you know behind the scenes in terms of what the classes are doing. And it is helpful. That being said, scikit-learn provides transformers for each of these. So it provides a standard scalar transformer class. It provides a min-max scalar. It provides a simple imputer class. It provides a one-hot encoding class. It provides many of these different transformers that you can use to perform these operations. Although knowing these ideas behind the scenes is useful when you're making decisions. So for example, when you want to choose between min-max scaling and standardization, you should have a brief understanding about what you're doing, what these transformers are actually doing. You shouldn't just randomly be using them. And so you wouldn't have to be required to do any of this math. Now, you should be able to program this math. It's not that difficult to program most of this math. Now, standardization might be a little bit more difficult to program compared to min-max scaling, but our goal is not to necessarily program these transformer classes. Now, you could program your own transformer classes and create your own transformer classes, and there is room for that. In fact, later on, I think we're actually going to be creating our own transformer class rather than using a transformer class that scikit-learn already has. But that is something that we will discuss in a future lesson. And typically speaking, that is for special use cases that are specific to our individual case. And right now, the stuff that we're going through is generally speaking stuff that the class already exists for that. Okay, so scikit-learn provides a standard scalar transformer. Now again, this does give meaning to the data. Now, what's the range of this data? You might be wondering. For the min-max scaling, it was between 0 and 1. Now, for standardization, what is the range? The range is, typically speaking, -3 to 3. Now, there might be outliers of the data, so there might be data that is outside of this range, but typically speaking, for most values, it will be within that range. Now, it still will give meaning to the data, even if some data is outside of that range, because the machine learning model can say, okay, this is data that typically speaking is not within an outlier in this case, right? So it's an outlier data. Now, if it is a bell curve data, typically speaking, if you did some normalization, work with normalization maybe in a statistics class, you may remember that this z-score, which is what the z stands for, z-score, is a value between -3.43 all the way up to +3.43. But in our case, most of the data will be between -3 and 3, and any data out of that, the machine learning model will be able to easily recognize that it is an anomaly, okay, an anomaly or an outlier. All right, so these are the two methods that we use for feature scaling. Now, what's the broad picture idea, big picture idea? Why are we doing feature scaling? Well, it's to make our data have meaning and give more meaning to our data, to our machine learning model, such that all the data is within that given range for every single field, rather than each field having its own range. That's what we're going to be doing, okay? So that's what feature scaling is. Now, with that being said, let's get into the coding, all right? Let's get into the coding now that we've discussed all of this, okay? So what we're going to be discussing here is transformation pipelines. Before we do that, however, I do want to discuss something, and that is our housing data frame. Our housing data frame. So our housing data frame, if you remember, we've modified this object many times, and we've actually given it different variable names in different instances. Now I want to talk about something with regards to storing these housing data, these pandas data frames, which is, remember, what we're working with, as objects. Remember what an object is. An object, whenever you create a new object, what you are doing is you are creating an instance of that object that is stored in your heap memory that has a unique address. Now, that is what you are doing when you're creating an object. You're storing it in your heap memory as a new instance of the data in your memory, okay, in your memory in general, okay? You don't need no heap memory, but it's within your heap memory, okay? Now, let's say you reference that same object with a different variable. That is still going to reference the same object. So let me go ahead and write something now. Let me go ahead and create a cell here. I'm going to go ahead and say C equals simple imputer. Okay. Now I didn't import it in this particular cell, but I said C equals simple imputer. I'm creating a new imputer class. Let me go up a little bit here and just take a look at something. All right. One hot encoder. Okay, good. Okay, good. So we created this particular class, and let's say we I'll copy this here. It'll be easier for you guys to understand. Okay. So if I do this here, you notice here that I have a one hot encoder object that I've just created, and I've stored it in a variable of cat encoder. Now remember, the variable does not determine where it's stored, does not create a new storage memory reference. Okay, so let's say I said dog encoder equals cat underscore encoder. This does not change the memory reference. This object right over here, cat encoder and dog encoder, they both point to the same places in memory, right? So they both point to the same places in memory, even though I'm using different variable names. How do I create a new cat encoder class? The way I would do that is I would say dog encoder equals cat encoder dot copy. This creates a new memory, a new reference in memory for this object. That is very important. So when I call this copy function, I'm creating a new place in memory, in our heap memory, for this particular object, a new location in memory. That is a very important idea, because when we perform operations on an object and we store another variable, even if that variable name is different, with that pointing to that same object, we are indirectly modifying all the objects that it's pointing, all the variables that are pointing to that particular object. Okay, so keep that idea in mind there. And with that being said, I'm going to go and take a look at where I'm talking about this. Okay, so let's go back to the beginning of our data frame, of the beginning of our Jupyter notebook here. Let's take a look here. We notice here that we did some stratified sampling a while ago. And when we did the stratified sampling, I believe we did right here. So we said stratified training set dot copy equals housing. Now I didn't really explain it that much at the time, but this created a new reference in memory. And when we printed that data out as our housing, keep in mind that it had all the different columns in our data, right? All the different columns in our data along with the income underscore cat. Now remember, the income underscore cat basically assigned a numerical output using different strata based on different strata for our labels, right? So if you remember that back then, we did it like that. We sorted that in housing. Okay. Now stratified underscore training set. Okay, this object right over here is stored in a different location in memory than this one right over here. Okay, and then we'll go down here now that we discussed that for a second. Let's go down a little bit. So now we have a housing and we have stratified underscore train set. Those are two different objects in memory. If I perform any operations later on the housing data frame, I'm not going to be affecting the stratified training set. Okay, so keep that in mind. So let's go down here. We did some plotting. Again, doing some basic plotting doesn't change anything. Okay, so let's go ahead and do this. All right, so we see here that we have a new variable here, housing underscore matrix, and we removed one of the columns. So now if I go ahead and print housing, okay, and based on what it should do is, okay, yeah, so it did not update it in this case because I did not set it back equal to housing. Okay, so keep that in mind. In order for me to update this, I'd have to say housing equals housing dot drop, right? I had to reassign it. In this case, I didn't reassign it. Okay, so it kept it the same. Okay, so let's go ahead and delete that there. And I'm just gonna walk through this a little bit. Something's wrong here. All right, let's go down. Median house value. And so then we have that there. So it didn't update that particular object. All right. And then if we go down here and we work our way down, we notice here that we then do this because this is what I want to focus on. Okay, so we have here housing rooms per household, and we're updating the housing data frame object, and we're setting it and we're printing it out. So notice here that we were able to get these different columns. Okay, so we got these different columns: rooms per household, bedrooms per room, population per household as well. And then we were able to drop the ocean proximity as well, the ocean proximity column, and set it as being correlation matrix. That's not really relevant because we're not reassigning it there. And then we have data cleaning, and we did that there. Okay, so right over here, we went back to the original stratified training set and we removed the median house value back to the original stratified training set. So that's a different object. Keep that in mind. Okay, and then we worked our way down. We copied that particular column, right? We separated into the labels as well as the descriptors or the predictors, right? So then we filled in the missing values. This is what I did here, was that I actually copied it down here as a variable. I said housing underscore SI for the simple imputer object. Here we actually did it manually for a particular column, right? We did it actually kind of manually without using the transformer. So I copied it as a new object here, so that way we wouldn't update everything else. Okay, and I did the same thing for this here. I did here housing underscore C, and I was able to drop the ocean proximity. Now I dropped the ocean proximity, but if you take a look at over here, let's say I run it again now, housing, even though I dropped that column, if I run housing over here, remember I dropped it and then I set it as a new variable by using the copy function. If I run this, I still have ocean proximity here. Even though if I look over here, housing underscore C, C just simple imputer, I just named an object there. Okay, you see that there. I created a different instance there. And even though I called the drop function for the ocean proximity, even though I did an ocean proximity, it didn't affect the main housing object that I created. It didn't affect that object. Okay, so keep that in mind. So now, if I run housing, what I wanted to do was I wanted to add the rooms per household and bedrooms per household. So I just wanted to do that as a part of today's tutorial. We have not added that in our code base, so you can add this in your code base. We're adding in the rooms per household and bedrooms per household and population per household into our data frame object. Okay, so keep that in mind. We're updating that. Okay, so now if I run this here, print housing, and I get rid of that, and then I run it again, you'll notice that we get those additional columns along with our ocean proximity. Okay, so then we did feature scaling, and now we're going to get back into transformation pipelines. So before we do this here, let me go ahead and show you what it looks like right now. So this is the housing data frame. We have all the data here, including income underscore cat, which provides us with a categorization for our median house value in terms of what strata it's going to be located in. Okay, so it provides all that data, and our goal is to convert all this data into numerical attributes that are scaled between 0 and 1. Remember that. Okay, so we're trying to scale everything between 0 and 1. Now keep in mind I have to remove the ocean proximity again because we have not actually updated the housing data frame. When we did our data analysis a while ago, actually, we were able to find out what the how to convert categorical data into numerical data, if you remember. So this ocean underscore proximity, we were able to convert that categorical data into numerical data. Okay, so we're able to convert that. Now, we did not actually update the housing data frame when we did that. In our next lesson, we'll learn how to do that using a pipeline, actually. We'll learn how to use pipelines. In today's lesson, we'll learn how to use pipelines, but we'll discuss the class that we can use in order to convert categorical data into numerical data, because that's very useful for us. Okay, so right now we haven't updated that. Okay, so we'll have to drop this particular column. And in our next lesson, we'll discuss how we can add on the data using a particular transformer that we're going to discuss in the next lesson. So we have all that data. Now we want to convert that again for min-max standardization. We're going to discuss what a pipeline is. So what is a pipeline? So far, we have used built-in transformers, such as, for example, one-hot encoder and simple imputer. And we have called the fit transform function on each of these for the data in order to predict and perform actions on our CSV file. Now, we've done that for each of our individual objects, right, that we've created. What a pipeline allows us to do is it allows us to perform a sequence of transformations such that the output from one particular transformation will affect the next transformation that we're doing. So let's take a look at this. It says here that it's going to make it easier to perform a sequence of pre-processing steps by allowing us to call the fit transform on a single pipeline object instead of having called fit transform separately on each individual transformer. So this is what I wrote for the description here. And then I also wrote, the pipeline is executed sequentially where the output of one step becomes the input to the next step. This is extremely important. So let's say we're working with our housing data frame object, and we're performing basically 3 operations on it. Okay, when we perform those 3 operations on it, the output of one of the operations will become the input for the next operation or for the next transformation. That is important. So like, for example, this is something like, for example, when you maybe first learned programming, you were maybe taught that if you had a variable x equals 5, and then you had another operation that said x equals x plus 3, and then you had y equals x plus 2, and you had to print out y over here, and then you had to print out x, and then you had to print out x. This is kind of what a pipeline is doing. So in a small sense, this is what a pipeline is doing. We're having x equals 5. Now, when we do y equals x plus 2, are we still assuming that x is equal to 5? No. We're assuming that x is equal to x plus 3, which means x is going to be equal to 8, right? So x is going to be equal to 8. This is what a pipeline is doing. It's basically taking the output from the previous step as the input for the next step. That's what it's doing. Okay, so that's what a pipeline is basically doing, and it's pretty simple for you to understand that. Okay, so we have a sequence of transformers. Okay, so I mean, I think you could technically have one transformer, but typically speaking, its use case is for several transformers. If you just have one transformer, then it's just better to keep it on its own, right? So what is the fit underscore transform function? We've been using that a while. Let's take a look here at when we used that a while ago, and let's take a look at what I wrote then. So remember, we used the one hot encoder to replace what do we replace again? I think we replaced the ocean proximity column with zeros and ones, right? Where one referred to, I believe, inland, right? And then zero referred to all the other values that were near the ocean. So, or near a bay. The fit transform function, we said, it learns the numerical attributes and replaces them with a number of 0 and 1. So it basically does really two operations. It does a fit step, and then it does a transform step. The fit step is when it learns the numerical categories, learns the data, and then the transform step is when it replaces the data or it does some operation on the data. Let's go back and take a look here at our documentation that I wrote here. Every time we run a scikit-learn pipeline, we have a fit step and a transform step. The fit method learns the parameters needed for the transformation from the data, such as the median used to fill missing values in the simple imputer. So it learns the parameters needed for transformation. Then the transform step applies the transformation to the data set using those learned parameters. Then the fit underscore transform function allows us to create do both these operations by just calling one method. So I hope you understand that. So the fit method basically learns the data, and then the transform part of the fit underscore transform function, it basically performs those operations using the parameters that they learned from the fit function. Okay, so let's take a look at this. So we're going to start off by writing our boilerplate code here by importing our different modules. We're going to import scikit-learn.pipeline, import pipeline, and then we're also going to import the standard scalar class. Remember, I referenced that when we do standardization, we can use the standard scale transformer class. So we're going to import those two classes, and then we're going to print housing just to reference this again. We need to remember drop the housing, the ocean proximity column, because we cannot scale it. We cannot scale it in any way. Now, once we insert the one hot encoder version of it, which we will learn how to do that in the next lesson using a pipeline as well. We'll get some practice using pipelines. We can do the scaling for ocean proximity. Although for ocean proximity, it's already going to be zeros and ones. So we'll see how we'll do it when we get there. Okay. So I'm going to say housing pipeline equals housing.copy. Why am I doing this? Well, because I don't want to affect the previous references of this particular object. I don't want to affect those previous references of the object. And so because of that, I'm going to create a new copy of the housing, or else I'm going to affect the previous references of the data. Okay, so, and this is a little bit different when it comes to objects in that, like, for example, if you create a new variable and you reassign a variable, that's not going to affect the previous variables, right? But in this case, when we're doing the object way, creating new instances of an object, if we alter an object in our Jupyter notebook, right? When we alter an object later on, it's going to affect the previous objects that we created if they're pointing to the same object. And so we're going to create a copy of it. And then we're going to drop the ocean proximity column. Now, why is it important that we drop the ocean proximity column? Well, because we need to drop the ocean proximity column from our new housing pipeline object. So we need to drop the ocean proximity column from our housing pipeline. Why is that important? Well, if we drop it directly from housing without creating a new object in our memory, if we drop it directly from housing, keep in mind here that before in our code, if we look back here, we are referencing the ocean proximity column using housing. And so if we drop it later on, it's going to affect the housing data frame in our Jupyter notebook. And that's going to result in this returning with an error because it's going to say the column doesn't exist in our data frame, right? And so we have to create a new reference such that we can alter that new reference without affecting the housing data frame. And so it's a little bit, when you're working with a Jupyter notebook and you have like going many cells over and over again, it is a little bit difficult because you have to use different object references and make sure you're not updating any previous object references either. So we're going to drop this column and axis equals 1. Remember, that's because it's vertical or vertical columns, right? Axis equals 0 is for horizontal. Then we're going to create a pipeline. So for the pipeline here, the pipeline, the way it works here is that we're going to have a list of tuples, right? So a tuple, if you remember, is simply a value along with another. It's simply values separated by commas, right? And it's typically speaking used to represent like coordinates or points. In game design, even they use that a lot. But in this case, a pipeline is simply going to be an object of a list of tuples. So pipeline is an object. Remember that. Whenever you have the parentheses, that means it's an object. Okay, you're creating a new object. Now in Python, you don't write new pipeline or anything like that. You'll just create it using the parentheses. So we have here a name. So the imputer is a name. Now remember, you could give this any name you want. You can name it anything you want, but we're gonna try to name it something that is related to what we're actually doing in the next section. So the imputer is going to be the first value or the first element in our tuple. The second element in our tuple is going to be the actual object. Okay, the actual object. So the object in this case is simple imputer, and the strategy is going to be median. Okay, so median is what we're going to replace all of our missing values for each column. And then also standard scalar is going to standardize each of the columns. Let's go ahead and get rid of that print housing for a second. Let's get rid of that for a second. Let's rerun that. Okay, so good. So then we're going to say num pipeline, which is what this object is, dot fit underscore transform. So what it's going to do is it's going to learn the data for simple imputer and standard scalar. And then it's going to perform the operations of replacing all the missing columns with the median value for each particular column, as well as doing standard scalar to convert the values, generally speaking, between -3 and 3. And then we can go ahead and print housing underscore pipeline. So the output, we're storing that in the housing pipeline class. All right, let's go and run that. So you're seeing here that we get a NumPy array. This is a NumPy array here, and each particular row is going to represent a district. Okay, so each row is going to represent a district. All right, so horizontal district there. So you're seeing here that you have all these values, and you're going to have roughly 6,000 rows in this case, 6,000 rows within our main list, right? 16,000 sublists, rather, I should say. And each row represents a district. So keep that in mind as well. All right. So taking a look at this data, you are seeing that generally speaking, it is between -3 and 3, generally speaking. So it is within that range there as well. So again, remember, why are we calling simple imputer before we call standard scalar? Well, the reason for that is because we want the data to have not have any missing values before we find out what the scaling is for each value. And so it is important for your data frame, for your pipeline, that you know what you're doing in terms of, the order, right? You know the order in terms of what you're doing. So let's say, for example, I were to do it the other way around, then you might run into some problems. Now, in this case, you might not necessarily run into problems because standard scaling would scale the values between between -3 and 3, and then you'd be finding the median among all those values. So in this case, it wouldn't really be no, it actually would not be. It would no, it actually would be a problem. Sorry, it would be a problem because standard scalar would have to work with missing values. Okay, you would have to work with missing values. So keep in mind the order at which you do the operations. So that's important. So the order at which you do the operations is important. Just like, for example, if you say x equals 5, x equals x plus 3, y equals x plus 2, then you have to know the order at which you're doing things. And you can add the print statements, right? All right, so that's what we discussed in today's lesson. And so we discussed a lot in today's lesson. I believe the video will go on for probably above 30 minutes or so. So it was pretty long of a video. But we discussed several things. And remember, at the beginning of our code today, we did insert these new columns in our data frame. So add that to your code base as well to insert those new columns to our housing there as well. So that's important there that you add those new columns. But we discussed feature scaling. We also discussed pipelines. And I will see you in the next video where